10 micron, the device size. Okay, so this is one of the work here. So here what we did was we used hafnium. It's a material which is known for its high spin orbit coupling, and we were able to generate. I told you spin orbit coupling leads to spin Hall effect and therefore leads to spin orbit torque. And because hafnium had very high spin orbit coupling, we were able to generate very high spin orbit torque in this work. Okay, so this I'll probably skip through because this doesn't matter so much. I will also just show a little bit of this work. So here we used topological insulator instead of, so in the first work we used hafnium. So hafnium was used, it's an element, it's heavy metal, it was used to generate this huge, the higher spin orbit torque because we knew it had a high spin orbit coupling. Okay. Now we also used something called a topological insulator. So some of, have anyone of you heard of topological insulators? Anyone? Okay, so topological insulators are a very interesting kind of material. Okay, now what happens in this kind of material is that, and this is also a very highly sought after quantum material. Now there are some certain materials which are sought after for quantum applications. Topological insulator is also one of this kind of materials. Now these materials are very interesting. These materials, they are insulating in the bulk. That means in the, if you take a conductor, okay, in the center, they are insulating. No current will pass through, no electrons will flow. But on the surface, they are conducting. Very interesting, right? So it is an insulator at the core. It is a conductor on the surface. So what is it? What makes it interesting, therefore, is that the surface states will very efficiently conduct your current. Okay, but the core is insulating, so you have very limited loss. Okay, the heat base, the joule heating, and all those electron transport based losses, they are minimized, and they also have very interesting properties in terms of spin because the electrons which are flowing on the surface, they face asymmetry. Okay, asymmetry in the environment. The environment outside and inside is different for them, isn't it? Okay, so because of this asymmetry, what comes is something called spin momentum locking. That means when the electron is flowing, its spin, for example, its spin is like this, it is locked. It will not change. It will flow with the same spin. In a normal conductor, when it is flowing, what will happen? Scattering, and it will keep on changing the electron's spin. But in this kind of materials, topological insulators, the spin and the momentum are locked. So the momentum is like this, the spin is locked to this momentum. If the momentum is opposite, let's say it's moving in the opposite direction, it will be in a different direction and it will be fixed there. It will not move. Okay. So the change in phase or change in spin of the electron doesn't take place. That's why it's very interesting for spintronic properties and transport of pure spin currents, right? Because now the spin will not change whatever because of the protection in the material itself. Okay. So bismuth selenide is one of these examples. Bismuth telluride, bismuth selenide. These are examples of topological insulators. Okay, they exhibit this kind of property called topological insulation. So the word topological insulation actually comes from the fact that topology. You know what topology means, right? Topology is more like the shape, the structure, or the topology. So that topology gives it the insulation property. So that's why it's called topological insulator. Okay. And these are examples. I have shown some examples here: bismuth telluride, bismuth selenide, antimony telluride. So these are materials which exhibit this kind of property. So what we did was, now here again I'm showing some of my work here. So these are material characterization because I told you that at this scale, material information and material characterization becomes very important for development of this kind of devices. So we first developed this material. This one selenide material was developed. When I mean developed, what I mean is that see, so a chemist, a physicist, probably you are all making materials, but you are making materials in different ways. Someone makes it a solution. A physicist probably use a physical vapor deposition. to be made. It has to. That's what I'm referring to as development. Now, what was done was initially it was never sputtered, so it was never used by or deposited by physical vapor deposition. It needed something called MBE, okay, molecular beam epitaxy. Some of you may have heard of it, some of you may not have heard of it, but it's called molecular beam epitaxy. This will enable you to grow layer by layer very smooth films, but this is super expensive and super time consuming, okay, and that is never liked by industry doesn't like these kind of processes because who has the money and patience for that? They would rather put 10 more factory lines and make something which is faster, right? So what we did was this was one work. It was published in I think end of 19 or 20. So we were able to develop this material using standard semiconductor compatible methods, which is sputtering in this case. Okay, so something that already the semiconductor industry has. Only then they will like this. Otherwise, they don't like this kind of things. So this is a very exotic material. Bismuth selenide, I told you, insulating in the middle, conducting at the surface. Spin is locked, so very good for spin manipulations. And we were able to develop it in sputter deposition. Okay, so that was the integral part of it. And here what here I will show you something. So what we were able to do is I told you. So someone asked me how do we know, how do we measure the magnetic property? So see, we never measure the spin of an electron. Okay, we always are interested in the bulk of it. Okay, so this is a device. This is a device. This is the center of it. Okay. Now you will see first thing is there is black and there is white. Okay, so the black is one direction of magnetism, the white is another direction of magnetism. It is indicated, okay, with an arrow, right? So this is two different states, 1, 0. Now, how am I measuring this? There are multiple ways of measuring. I showed you an MFM measurement before, the red and the yellow graph, right, or the orange and the yellow graph. That's MFM. Okay. Now there we measure the magnetic field near something and we make a map of it, so that we know which one is in which direction. Here we are using something called a Kerr microscope. So this is a optical based measurement. Okay. Optical measurement. So light itself is also sensitive to spin. So many of us probably don't think about it, but light itself is also sensitive to spin. So when light is falling on this material, it is able to either reflect back or getting absorbed based on the spin of the material, okay, or the magnetism of the material itself. So light can also be used to measure this. Some kind of setup will be needed for that. So there is a Kerr microscope. That Kerr microscope is needed here. So what we were able to do is we were able to switch it from this direction to this direction. You can see, no? This is one direction and then this is two. Okay, so we are applying a current. This is the I current. We are able to apply a current like this. The current is passing below it, and the current passing below it should switch this one. That is SOT, right? That is what I said is SOT, that the current is passing in this metal layer. It will change the orientation of the magnetic layer. That is SOT. So we are passing a current below this, we are this is the top view, but here that metal layer is there, and the current is passed to the metal layer. This is the ferromagnetic layer. The ferromagnetic layer is black here, which means one direction, let's say up direction, and by passing the current, we are able to switch it to the white. That means the down direction. Okay. Now, if I remove the current, it will retain this position. It will not change. Again, if I pass the current in the opposite direction, I will again switch it back from the white to the black. That means to the down to up and then up to down. Yes.
So you just mentioned that light can be used to modify these characteristics. What type of light are we talking about?
So when I talk about light, I am talking about any optical light in the optical range, in the visible range. Okay. Sometimes near infrared also, and because those lasers are generally used, the near infrared or infrared lasers are used, and some in the optical range also. Now, what happens is that this light has this property. I mean, you are all familiar, right? You are familiar with the So light has polarization, you all know about it. Now this polarization of light actually is influenced by the spin of the material that it is falling on. So for example, I have one material, I have a light coming in. Generally, a light is not polarized. But if I use a polarizer, I can pass a polarized light through that lens. Right? Only polarized light goes through. And certain I can choose the polarization, whatever polarization I choose. That light goes there, and then when it is coming back, its polarization will change. The polarization of light will also change because of interaction with this material. And then when it is coming back, I can again measure it, compare it with the reference, and I will know how much it has shifted its polarization, right? So that way I can use it for measurements, and this effect is called the Kerr effect. If you are interested, you can Google KERR Kerr effect. So Kerr effect is used for this microscope here. So this is that's why called MO, okay? Magneto-optic Kerr effect. Okay, so this is again another method to measure magnetic state, right? So here we were successfully able to demonstrate that how bismuth selenide, this topological material, can be used for this bismuth selenide topological material can be used for uh, SOT, spin orbit torque. Okay, why is it important? I told you the bismuth selenide is insulating in the bulk, conducting on the surface, has spin momentum locking, and therefore I have excellent, at very low current densities, we are able to switch the magnetization. Okay, so that's why this work was very good for us. Okay, so anyway, I hope I have been able to give you some idea about how these things operate. So let us now go into, this is another slide. It is showing a difference between spin transfer torque and spin orbit torque. Transfer torque is applied through the layers, okay. Orbit torque, the current is applied at the bottom layer, the torque is applied in the perpendicular direction, okay. So, same slides. You are going to share, sorry. Are these slides being shared with the participants? Yes, right. Okay. So then you will be able to see it at your own time also anyway. Okay, fine. So I already talked about this STT and SOT. All right. Next SOT. Okay. This is a sideways discussion, but I'll just mention here. See, this is the Hall effect. We all know, right? Magnetic field applied, charge separation. We know that. This is there are different other Hall effect. This is anomalous Hall effect. Then there is the spin Hall effect I just now talked about. Okay. Then there is quantum Hall effect, quantum anomalous Hall effect, quantum spin Hall effect. Okay. Multiple kinds of Hall effects are there, which are already known, and they have been eventually discovered. 1879, 1881, 2004, 1980, different. Okay. All right, so introduction to spin-off law effect. Okay, so maybe I just talk about this for a few minutes. So I mentioned the spin Hall effect, and I told you that spin Hall effect is helping in this SOT that leads to the SOT. So let us see what the spin Hall effect is. So you see, when this current is passing here, because of the ferromagnet I showed you, the spins are separated, right? The red one goes here, the blue one comes here. Okay. Now, this is why is this occurring? This is occurring because of preferential scattering. This is happening because of preferential scattering. I told you in the beginning, no, that this GMR effect, for example, that when the current is or the electrons or the moments are coming, if the guard or sees similar people they like, then they will let go. Otherwise, they will scatter them, right? So same thing is here. So this is spin dependent scattering. So what happens is these two electrons are coming here. Okay, one has upspin, one has downspin. At this scattering center, now this scattering center can be an atom or anything, but this scattering center will scatter this in this direction and this will scatter it in this direction. That's why the charges are getting separated. Not the charge, but the spins are getting separated. Okay, so this is the spin Hall effect. Okay, this is clear or
Yes, is this immediately above the current or it's
this is a normal current, just a normal current having electrons which can have any kind of spin, up, down, in any proportion. Generally, they are more or less 50-50, but it can have any direction. And when it is passing, you also know that it will constantly keep on changing because of scattering in the matter. But at the interface where the metal and the ferromagnet is, at the interface, it will get scattered preferential. So if this is the entire metal layer, then at the most of the metal, the current is passing in a normal way, scattered everywhere. At this interface, that's called junction. There it will scatter differently. The two electrons coming will scatter differently. Okay, based on their spin. So this is the spin Hall effect. Okay, anyway, so we talked about this analogy before, and maybe you when you look at the slides, you will have a better idea. Okay, so I will skip through this. I already discussed this kind of device. Right? I already discussed. Only difference now is that instead of a field being used here, we will use STT or we will use SOT. Okay, so I will skip this ones for now. Um, yeah. So again, this is the comparison. So the first slide where I showed you these three different mechanisms is just a comparison here, and you can read here. I mean, but I already mentioned all these things. That in here the magnetic field is used as a writing thing. A current is generating the magnetic field. Here spin transfer torque. Here spin orbit torque. Okay. And the advantages are here less heat is generated because the right current doesn't pass through the entire layers. Okay, in spin orbit torque, the right current is passing only here, only the read current goes to the device, right? That's why we have less heating effect here. Okay. Okay, so these are the companies that are already working on it. They have developed an MRAM already. So I just thought maybe if some of you are interested, you can also look into that. Okay, so I will not discuss this, but I will tell you that someone asked me actually that why is damping important. Okay, so see, generally we always want high damping because we want it to be stable. No? We don't want it to be moving like this. However, in some cases, for example, here we want to generate oscillation. So this is called terahertz generation using SOT. Here I want the oscillations. Okay. Similarly, you will, there is something called okay, morphic devices. Spin torque oscillators are there. These are oscillators. Okay. Here I want oscillation. So here I will use a low damping material. So high damping, low damping, both has uses. In memory, in sensors, we use high damping, but in oscillators, in terahertz generators, we will use low damping. Now these are again devices which are using SOT. I discussed SOT today. SOT is a phenomenon, right? Now SOT I discussed today in light of only the memory device, only the MRAM. Okay, but the same phenomenon can be used for terahertz generation. Terahertz is very important because 6G communication goes into the terahertz range. Okay, so there you will need generators, and these generators can be spin based. SOT can be used for that. Second is oscillators. People who are from electronics locally will know that these VCOs are used, voltage controlled oscillators. Voltage controlled oscillators have their own limitations. They are very bulky. They cannot be integrated in very small circuits. So there again, these spin based oscillators can be used. Okay, they use spin orbit torque. Okay, so different applications of spin orbit torque can be there. I have not shown the biomedical ones and so on, but multiple uses can be there. Okay, so we will move to the next topic after that. But before that, do you have any questions so far? I know I have rushed through some slides, but I have tried to give you the most important information. And when you read through or you refer to the slides whenever you are interested, maybe you will get more information when you want it. Obviously, after that, there is ample information on the internet, so nothing stopping you. Any questions from this part, the previous part?
So for the characterization of the spin,
Hmm.
when we apply a particular wavelength of light, then there is
That optical based, you
yes.
say.
So
Okay.
if I am applying, suppose a TE polarized light into a, I want to change the orientation of the spin.
Hmm.
What is the way you characterize that?
See, I did not. So, so you said that change the orientation of the spin. Right? Okay. See, I never mentioned this so far that light can also be used to change the orientation of the spin also. I never said that, but you said that. But that is true. That can be done. So what I said was that when this polarized light is going and interacting with the film, the polarization can change. and when it is reflected back, I can sense this polarization change, and that's how I know the magnetic state of the material. And when I am being very conscious in carefully using the word magnetic state and not spin. Why? Because when I say spin, it is refers to one very small. But when I say magnetic state, it refers to a region. Because, for example, you are using a light source, right? You are using a laser. So the beam spot itself will be a few millimeters. So you are sensing the entire region, isn't it? So that we have to think of. Okay. Have I answered your question? Yes. Okay. Okay, so if no further questions, then we'll move on to the next topic. Okay, so in the next topic, again in the beginning, it will be mostly the fundamental things I am mentioning. All of this can be found on the web, nothing proprietary to me. But towards the end, I will show you some device which probably can be original to this one. Okay, so before that, it is more generic. And maybe most of you are already familiar, and some of you who are from physics probably knows better than me on these things. But nevertheless, I will just cover for the sake of the general audience. Okay. I don't know why it is. So yeah, light is a wave. That was the initial question or initial answer, right? Everyone knew light is a wave, and it was also shown by this Young's double slit experiment, which all of you are familiar with. That light is a wave, right? So that's why we are able to generate these interference patterns, right? Right? All everyone on the same page, right? Next, some people were confused towards the beginning of this century that why does light also have something called the photoelectric effect? Photoelectric effect we all are familiar with. Okay. Uh, Professor Einstein also got the Nobel Prize for that, right? So we were all wondering when I was not born. They were wondering. The humanity was wondering why, right? So that means light also has to have some kind of particle nature, right? And the physicists of those times, including Bohr, Planck, all of them started to wonder if it has this particle nature, and eventually we ended up on the understanding that it is dual, right? It has dual nature. It is a particle as well as a wave. Okay. So again, this is all very generic. You all know this. Now, this brings us to the quantum nature, therefore, right? Where we have both wave phenomenon as well as particle phenomenon. Both of them can coexist, which could not exist or which could not coexist in the classical world, right? But in the quantum world, they coexist. And now, what are the properties? What are the essential properties that identifies with a quantum phenomenon or quantum materials or quantum word in that sense? So one of that is the superposition, right? That term superposition. Now, again, many people probably are familiar with the Schrodinger's cat, right? That means is the cat alive or dead? The question was is the cat alive or dead? Can never be known unless you probe it, and the moment you probe it, it will either end up in one of the states. Okay. So similarly for any quantum material, it is not in a zero or one state that we want it to be. Okay, so I told you the upspin and downspin, right? It is not always in the upspin and downspin. It is always in a superposition of both. Okay, the moment I try to probe it, it will collapse into one of them. Only when I try to probe it, it will collapse into one of them. That is the fundamental understanding or fundamental concept with superposition with quantum nature, right? So it exists in both states, right? So if it exists in both states, then that gives us very interesting properties from the technological perspective, and that we will come to after this. So this is the first thing. Second thing is the quantum probability. So now first thing was that it exists in superposition. Now the second thing therefore is what is the probability, right? So probability in this case, for example, is shown in terms of the possibility of an electron in the vicinity of a nucleus, right, or proton. So what you see is that the probability goes lower and lower as you go away from it, right? But it is not zero. Okay? In quantum, there is nothing zero. Never it is zero. It is always, it can be infinitesimally small, but it will always be there. Right? The probability still exists. Okay. So then there is this probability. For example, if I have a wave function, if I have a wave function for an electron, so you talk about a photon, you talk about electron. So if an electron has a wave function, so the wave function is it can determine its superposition state, but the probability of that thing being there, how do you find that? So that again is mathematics. So generally it is depicted, sorry, I'm not shown it here, but it is depicted as the square of the wave function. Okay, it is depicted as the square of the wave function. So that is a quantum probability. Then there is the phenomenon which all of you again have heard about, because this is very fancy. It's called quantum entanglement. Right? You can keep reading it here and there. Quantum entanglement. Einstein called it what? Spooky action, or action at a distance, something like that. Right? So basically, that one particle here. Now here I'm treating it as a particle. One particle here and one particle maybe 10 centimeter away, or 10 kilometer away, or light years away, will be entangled such that the change in one of them will correspond to a change in the other. Okay, this is like the Jurva movie. So probably Jurva children are born like that. Huh? I don't know. They have quantum entangled states, I guess. I don't know. But that is entanglement. Right now, it's a very difficult concept to think. I cannot get my head around this concept. Okay, probably if some physicists are there, probably you can help us understand it. I cannot get my concept around this, my head around this concept, how this happens. But apparently, people have already demonstrated this kind of effect, where one photon, one single photon, that's very difficult to generate, one single photon, and you change, make a change in the state of this photon, and you are able to see a change in another photon which is miles away. That has already been demonstrated so far, so we have to believe that it is true. But I cannot get my head around it, how this happens, but it happens. Okay, so another thing, quantum entanglement. Now, why this is important? Imagine now I can transfer information at infinite speed, right? If I make a change something here, I can make a change somewhere else, kilometers away, light years away. It also opens the door for all sci-fi movies. It opens the door for teleportation, right? Probably our ancestors never thought that we can see someone online through something called internet on video calls, right? And probably we are not imagining that our future generations probably can transport someone from here to the other place by this teleportation method. But possibly, maybe it will be possible, I don't know. But this will be an important part of that. Okay? This will be an important part of the quantum entanglement. Okay? Next is quantum tunneling. So this is something I still understand a little bit. But the first one I don't, the previous one I don't understand at all. My brain cannot comprehend it, but apparently that exists. So quantum tunneling, another phenomenon in quantum world, and I already I think talked about this. I showed that water barrier. You can also think of it like this also. So there is a barrier; it cannot go through in a classical sense. Like here, right? It has to only go above it in a classical world. In a quantum world, it can tunnel through. There is a probability, very small probability, but there is a probability. In a classical sense, there is no probability of it going through. In a quantum sense, there is a finite probability, maybe very low, but it is there. And it is also something like this, another cartoon to show it, that you can either pull it all the way, use a lot of energy and cross it, or you can dig a tunnel and cross it like that. Okay, so quantum tunneling again is very used today already in the devices I told you, TMR based tunneling magnetoresistance based devices. I have not used this word so far, but maybe it is time I use this word called magnetic tunnel junctions. Okay, so again, see, quantum world, spectronics world related. Okay, magnetic tunnel junctions, they are based on the TMR principle. Okay, and magnetic tunnel junctions have already been used for many sensors, many devices already. Okay. So quantum tunneling, another feature of the quantum world. Okay. Then is the quantum confinement. Again, this is something I can still understand. So quantum confinement, some of our chemist friends, if they are here, they probably already do this. Some physicists will also do this. So if people are working, so what is confinement? I mean, confinement we all understand, right? What is confinement? It's to put something in an enclosed space. Okay, and in this case, we make the space smaller and smaller. Okay, and what happens electronically with that is that the states, so in electronics we generally talk about bands, right? Conduction band, valence band, right? Conduction band, valence band. What is a conduction band consisting of? You all know conduction band will consist of multiple energy states like this, isn't it? Now, the moment I start making the dimension smaller, this energy states start becoming discrete and discrete and discrete, right? They become more separated. You know, instead of a band, they will exist as discrete states. Also, the energy band gap can be tuned, right? The band gap can also be tuned. So this is of quite a lot of interest, for example, in the photonics world, in optoelectronic world, in quantum dots. Have you heard about quantum dots, or have any of you seen a quantum dot based product? I'm pretty sure you have seen quantum dot based product. No? Huh? QLED, exactly. All of you have seen QLED. All these TV showrooms today, they have this big signs QLED, QLED, QLED. So that's quantum LED. Okay, and that uses quantum confinement. Huh? That uses quantum confinement to enhance certain properties. Right? The LED properties can be enhanced by this confinement. Okay, so QLED is already a product like that. So quantum confinement is another important parameter or important, let's say, term that is used in the quantum world for technologies. Okay. So band gaps can be modified. So that means the light that, for example, if I am creating a LED, the light that is emitted can be modified, right, by changing that band gap. So all these kinds of modifications become possible when I do quantum confinement. Now, what kind of confinements can we think of? What do you think when I say confinement? What does confinement mean? Like physically, how will it happen? 2D, 3D, right? So currently, where everything is 3D. Well, not everything, but most of the things. Next is 2D. So we are in 2D. The two dimensions, the lateral dimensions are still big, but this dimension, let's say, goes down. The thickness, let's say, goes down. So one dimension goes down, and then if the other dimension goes down, okay, then it becomes a quantum wire, right? Then if the other dimension goes down, it becomes a quantum dot, right? 0D. Okay, so you can shrink it in all directions. Now, how do you do it physically? Some of you probably already know, maybe you are researching on that already. But for others, how do you do it? Just give me, just throw ideas again, brainstorm how to do it. Let me put the question other way. When I say confinement, is it like I'm creating some kind of a physical box and confining it there? Say when I say quantum where, what does that mean? It's a physical where? Yes, no. See, this confinement, I will just take a few minutes here because I think this is important. Why you want to research? Because this is a research intensive topic, and if you want to research on this, then this concept will be very important. And maybe this will give you a lot of ideas. So confinement can take place in three ways, huh? Not three ways, many ways, but I'll talk about three ways here. So you want to make a wire, okay? Say you have a material like this. You have a huge material like this, and this is the blue material, okay? Everything is blue. This is the blue material. Now you want to make a black. You want to make a quantum wire out of it. So one way can be that I physically take away the rest of it, right? I physically take away the rest of it and physically cut out this well. This is one way I can make a wire out of it. So this is a physically done. So lithography wise, I can do it. I can make a quantum wire, right? Some there are some ways where you can actually deposit a quantum wire, but this is one quantum wire. So this is physically done. Clear? Now, what if I have the same sheet? I deposit or I dope, let's say I dope something here which is black, okay, and I again dope something here which is black, right? Okay, so now this is another quantum wire, but physically this is the entire sheet, isn't it? But I have carved out a quantum wire out of it by material way, right? I have changed the material. By changing doping, I can change the material property, right? Or by some kind of alloying or something, I can change the material property here, make it black. I can change the material property here, make it black. This is a quantum wire now, yes or no? Because this has unique property compared to this. If I have carefully chosen my materials, then I will know that the electron cannot go from here to here. So it is confined, right? So another quantum wire. The third one can be, so I have mentioned two ways now, physical, material. The third one can be, I can use a, on the same one I'm showing, or maybe I'll just draw the one. The third one can be, I can create a channel of just electronically, I have flooded this with positive charge. I have flooded this with positive charge. In between, I have a channel which has a confinement, isn't it? So this can be electronic. So this is Coulomb. So this is called Coulomb confinement, physical confinement, and material confinement. So these are ways in which you can create this kind of lower dimension materials in multiple ways. Why I am saying it is, many of you probably doesn't have access to lithography techniques, isn't it? It is quite possible. India doesn't have so much of lithography or patterning abilities in multiple institutes, right? But this one gives us a very this options by material changing, by charge based confinement. We can do we can create lower dimension materials in these ways as well. Okay, so that's why I thought this is very interesting, and some of you might have some interesting ideas using this. Okay, yeah, and because of that, you see the density of states will change. Instead of being a continuous one, it will start being discrete, and then for 2D, 1D, and 0D, we see that the states are density of states are changing with respect to the electron energy. Okay. Again, the same thing here. The equations are there. Let us ignore the equations for now. You will find it in any book if you want to. But basically, as we change the dimension of the material, the quantum or use quantum confinement, the density of states with respect to the energy graph will keep on changing like this. Okay. Okay, fine. Yeah. So this now this concept of a potential well, another concept which is being very widely used for in the quantum world is the potential well, right? And this is the example that is generally discussed is of a typical hydrogen quantum well, right? The hydrogen atom. Okay. So again, I will not go into the details here, but you can imagine that this is a region, okay, where there is this potential V, and here also this potential V, and in the middle the potential is quite low or zero, okay, and therefore this region 2 will serve as a quantum well, okay. Now this quantum confinement that we talked about, right, this is exactly like quantum well, isn't it? Because in this region, say if I use the material one like this on the board, if you see this this side this region will have a certain potential, this region will have a certain potential, and this region will have a completely different potential from its surrounding, so then it will form a well like that. Okay, so this is exactly the representation of this, okay, quantum well. And therefore, in this quantum well, we can this is the Schrodinger's wave equation, which represents the state of the electron in this quantum well, for example. And using that and working on that mathematically and all, you end up finding that there can be four discrete energy or levels here, one, two, three, four, and corresponding to each of them, this is how the wave function of the electron will look like. And corresponding to the wave function, these are the probabilities of this electron. Okay, so the wave function square will give you the probabilities, and you will see where the electron can exist. So one example you can think of is like you see this crest and trough, right, or up and down, right? So in both cases, the electron exists here also, here also, here also, here also, right? Okay. So this is the quantum well phenomenon. Again, you can read about it in more detail. I cannot go further than this here, but I hope you understand the gist of it, how physically or mathematically this is expressed using the Schrodinger equation. Okay. And yeah, so from here, where we have discrete energy bands, in a single dimension system or a zero dimension system, you can have this kind of quantum where you have discrete energy states. The electron can occupy discrete energy states. Okay. We all some at least many of you probably know about the EK diagram. So it can have certain combinations of energy and momentum k. So EK certain points are possible, right? Now if you look at the energy band formation, so what happens is these discrete energy levels, they start coming together. So you have one quantum confined 0d, let's say quantum dot. You merge all of them together, right? So all one, two, three, four, and numerous. So when more of them come together, so many quantum dots come together and merge together into one bulk material, then we have the energy band formation. So the discrete energy levels, they come together and form the energy bands, right? So because we have always studied the energy band, right? But it's actually the opposite. The energy levels form the energy band, right? We have never gone to the bottom of it to realize that all the energy levels together, they come together to form the energy bands. Okay, but if you have 0D materials or 1D or 2D materials, you might be able to have discrete energy levels, and that is very interesting in the quantum world to have discrete energy levels. Okay, and again the same thing that probably some of you already know about this, that this same energy k or ek relation, right? This is the energy and this is the k. If you have the ek relation, from the ek relation you will be able to actually find out where the energy gaps come. So anyway, I mean, I will not go into details of this one, but basically you will see that there is a cost function here between the which relates the energy and the k. Okay, so you will be able to find that there will be certain regions where it will cross the permissible limit. So the gray line is the permissible limit of the cost function. So wherever it is exceeding the gray lines or the gray dotted line, and those places the energy gap comes. There is no energy, there is no possible state here. So here, no possible state, no possible state, no possible state. So those energy gaps come into formation from that. This is the mathematical expression of this. Okay. We will not go into detail in this one, but if you are interested, you can find how the EK relation or from where from the Schrodinger wave function, how we reach this energy bands or energy gaps. Okay, so basically what I'm trying to do here is that I'm trying to relate the knowledge you already have to the quantum world in some way, so that you can find where the relation lies, because quantum is not a different world altogether. All the classical things we know is actually a manifestation of the quantum world. Only that the quantum world manifests itself in the classical way, depending on the environment it is. Is it bulk? Is it small? Right? What is the point of observation and so on? But the quantum world is no alien to the classical world. It is among us. It is around us. We are all made of the quantum world. It is just that at what scale we are seeing. If we go all the way inside the cell and everything inside, the molecule inside the atom, you will visit the quantum world. Just like I think how many of you have watched the Ant-Man movies? You have watched? Anyone? Yes, watched, yeah. So they go all the way to the quantum world. They have a very, very funny quantum world, by the way. But that's what they're trying to do there, right? They become smaller and smaller and smaller. And at some point, they say, oh, if I shrink further, I'll go to the quantum world. And they end up in the quantum world. Somehow, quantum world also ends up having some kind of alien species and humans and all. I don't know how that happens. Their imagination, but fine. But that's what it is. We are all made of the quantum world. But on the as the scale goes up, we are in the classical world. Okay. All right. So this one, I'll next go into the applications. Okay. So then there are these quantum electronic or quantum optoelectronic devices, and then there are this is one of the TM image of that of an image like that. Not mine, borrowed from somewhere. Sorry, I don't have the reference here. But yeah, so here we harness the same properties like the superposition property, entanglement, tunneling, right? These are the properties that we harness in this kind of quantum optoelectronic or quantum electronic devices. Here, I have presented or tried to present some of the differences between a quantum and a conventional electronic device. So, for example, in a quantum device, what will happen is that it will exploit the superposition principle, and therefore it will allow, for example, qubits or quantum bits to exist in multiple states. So that means a bit is no longer in 0 or 1, it is in a superposition of 0 and 1 in a quantum bit. Now, what that enables is that it enables parallel processing. Okay, so that is not possible in the classical world. Okay, so this is, for example, one difference by taking an example of the quantum bit, how superposition can be used. Second is, for example, entanglement. So quantum devices can use entanglement, and as I said already, the demonstration has been done that a photon here, changing a photon here can change a photon there, which basically means I can communicate at the quantum speed, right? Currently, my classical ways of communication are limited, right? We talk about 5G, we talk about 6G, and we talk about higher speeds, but these are like very limited, okay? This kind of communication. So today, if I want to send a radio signal to some kind of a probe that we are sent into outer space, right, beyond our solar system, it will take me years for that information from here to reach there. But by harnessing the quantum properties, we might be able to do that communication in jiffy like that, right? So that's where the quantum electronic devices are different from the conventional devices. Third thing is quantum devices again use interference, okay? But again, interference cannot be used by the classical devices. Fourth is quantum devices harness tunneling. So if I take the simple example of a GMR and a TMR, so GMR is a classical device, right? It doesn't use tunneling; it uses simple conductivity across a metal layer, right? In TMR, I am using tunneling. My electrons are tunneling through the insulating layer, right? Now that gives me, I told you, a big advantage in terms of noise immunity, right? It gives me higher sensitivity. So already we see how quantum effects can help us to overcome the shortcomings in the classical devices. Okay. So here I have tried to capture some different kinds of quantum optoelectronic devices. So this is not an exhaustive list. There will be other devices which exist, but I have tried to classify because if you don't classify, it is very difficult to understand. So I have tried to classify. So quantum transistors, okay, these are not conventional transistors. Here, instead of a conventional transistor, we still have a gate, source, and a drain. But this island that you see, this is a quantum confined feature, or say quantum confined structure. If it is physically confined or Coulombic confinement, it doesn't matter. It's a confined structure, and sometimes it's also referred as a single electron transistor. Okay, so instead of having multiple electrons here, you will have a single electron, and because you have a single electron, you will have discrete energy levels that are permissible, and this therefore will have a lot of advantages in terms of lossless, you know, lossless operation. It will also have advantages of the superposition, where it can be used for computing, computing in the parallel manner and all those things. Okay. Second is the quantum laser. Okay. Third one is a quantum wire, which we have shown here, right? Similar like this, a quantum wire, quantum dots, superconducting interference devices, SQUID. Have you heard about this one? SQUID, superconducting quantum interference devices. So you all know about superconductors, isn't it? Superconductors, you know that this is lossless transmission, right? You are able to transmit electricity without any loss. So that's superconductor. And they use some kind of device physics there. They use Cooper pairs and all Meissner effects and all. But let's forget about that. But point is, I can have lossless transmission. Now, here this is a super, and the advantage of that is that they have very high sensitivity when used as a sensor. So if I have a superconductor material, I am able to conduct electricity, and some kind of a junction is made here. If you can see, circular junction. So current comes here, goes both ways, and then goes out. Okay, one will be the reference, probably other one will be where you are sensing it. Okay, and these ones are very sensitive. They can sense a lot of change. So, for example, this squid, the super quantum interference devices. How many of you know about this Josephson's interferometer? Heard about this? Optical based. Mach Zehnder. Heard about this? Okay. So these are all interferometers, right? What do they do? They use interference, right? Light comes, one is probing, the other one is reference. They interfere, constructive, destructive. From that, you know what is the sense data, what you have sensed, right? Mach Zehnder or this one, whatever interferometer you use. Here also it's a similar principle, but it is using a superconductor and it is using electrons instead of light, right? So instead of optical cable, we have a superconductor here. And the current is flowing through it. It is sensing in one arm, it is referencing in another arm, it is interfering, and this interference is quantum. Quantum in only the quantum world electrons can interfere, and because of that, we can measure that what is the change. And this is very sensitive, it's very sensitive measurements. So squid, okay, superconducting quantum interference devices, and they can also be used to conduct very high sensitive magnetic measurements as well. Okay, and then finally the quantum bit, right? Quantum bit, two bit, very buzzword. Every day news you will read about quantum computers, quantum bits. Every company is making a quantum computer. Most advanced universities abroad are making quantum computers. We are also trying to make one, right? So quantum computers. 50 years back, 40 years back, supercomputer was a big thing. Everyone wanted to make a supercomputer. So now everyone wants to make a quantum computer. Probably we hope that someday we'll have it in India and probably Guwahati itself, right? So that's a dream. But, hopefully we'll all be able to work together for that. Okay, so quantum dot transistors. How much time do I have? So do we have a Q&A or I can go on all the way till 12 or do I need to stop before? I can go all the way till 12, no? Fine. So quantum dot transistors, I already talked about it. So see, how can you make this island? Is you can make it structurally. We already discussed structural here, no? Three ways: structural, Coulombic, or by heterostructure. Heterostructure is where I have different kind of materials on the sides, right? I have two kinds of materials on the side, and by that I confine that properties in a single channel, right? Similarly, I can confine it in a single cube or a very small region or island, and that can be a quantum dot transistor. This uses single electron effects, and therefore they can have all those superposition and interference and everything on it. And superposition and all those things can be harnessed there, and therefore they can be used for making qubits as well. Now, currently qubits are made in two ways, as far as my information goes. Qubits are made with the single electron transistors. At the same time, they are also used to making with this other one, superconductors. Okay, so both of them are being used to make qubits so far. Then quantum laser. Okay, so quantum laser, I don't work in this field, so I cannot give you more details about it. People who are interested in this can please look into it more. But quantum lasers are more actually interesting for communication, teleportation communication. Okay, and I already gave the example where single photon entanglement is already studied, right? So another area where they are important is quantum key distribution. Okay, so this is cryptography. So you already know about different kinds of cryptography. So in the quantum world, there is also this thing called the quantum cryptography, and their quantum key distribution is also a important or a very researched upon thing. Okay, so quantum key distribution is also achieved through quantum lasers. Next is the quantum wares. Quantum wares again very simple that you have confinement. So all the possible quantum properties are used here. And here is, for example, quantum confinement is done. band gaps can be changed, size dependent conductance. This will conduct in a different way because of its size, right? So those things come into the picture, and it is already used in, or let's say research for use in high density storage and in quantum computing. So these are the uses of, for example, of quantum wear at this point. I talked about the squid some time back, why superconductors are used, and they have zero resistance. They can current can flow through them very easily. They are used for quantum sensing, and they are. This is a Josephson junction. I mentioned the Josephson junction. This is a material is superconductor, but you make a junction like this, okay? And that is called the Josephson junction. And Josephson junction is used for quantum sensing, okay? So many sensors are being developed. If you follow the news, you may know that this government of India has initiated something called the quantum mission, isn't it? And they have three different verticals or four different verticals of that. If you are interested, you can look up on that. And one of the verticals is quantum sensing and meteorology. Okay, so all the sensing and meteorology applications can actually be moved into the quantum world where higher sensitivity can be found and noise free, all those benefits are there. Another one is quantum materials, material development basically. I think the other one is quantum computers or qubits. Forgetting the fourth vertical. So they have initiated in four different verticals. So if you're interested, you can look into that. Both from your research perspective and both from the perspective of how this can be, how the students can be connected to this. Okay. Okay, and then finally yeah, sorry, I don't know if okay. Finally, the quantum bit. Okay, so I told you the quantum bits are realized currently through single electron transistors as well as, or quantum transistors, as well as through superconducting bits. Okay, so they harness those same properties, superposition, entanglement, and the qubits can be, they've written here, the qubits can be superconducting qubit, it can be transform qubit, flux qubit, phase qubit, and all of them have their own advantages and disadvantages. Think of them as different kinds of bit in the current. So, for example, we have land, we have solid state devices can be dynamic, static, all those things are there. Similarly, you can think that there are also bits, but they are all different. They are harnessing quantum properties in different ways. Okay. Yeah, so qubit versus classical bit. The differences are quantum state. One exists in a superposition state. The other exists in very discrete, different states in the classical one. Entanglement is possible in the quantum world, which is not possible in the classical world. Measurement. So qubits, they are more probabilistic. I told you, right? They are more probabilistic in nature. Classical ones, they are not probabilistic. Uh, and yeah, parallel computing becomes possible with qubit. So, for example, a 128 qubit computer can perform, even 128 probably is not needed, probably even lesser than that, we will be able to beat our supercomputers easily. Our supercomputers, which are like huge, right? They cannot compete with even a 128 bit quantum computer because of the property of parallel computing, which is possible. So it can have parallel processing at the same time. All of different outcomes will be assessed at the same time. Otherwise, for example, what do your supercomputer do? Your supercomputer goes in a tree-based manner. Computer science department people are already here, so probably you already know about this, right? You go in a tree-based decision-making process, right? So you probe something, not to go here like that. You make a decision tree, and then you do a tree-based probing of some problem, for example, to find solution. In the classical one, all the tree branches can be traversed at the same instant, parallel, right? Your computer will process all the outcomes parallel, right? So that's why it will beat supercomputers any day. Okay. Okay, quantum applications. Then finally, I have 5 more minutes. So yeah, in this picture, I have tried to again. I borrowed it from some paper. I have to write the name. Refer it, but disclaimers. Many of these are taken from different places, and I have tried to include the references in most places where I have missed. I'm really sorry. They are used in imaging, sensing, computing, communication, encryption, navigation, atomic clocks. Okay, so all of them use the quantum properties and qubits, right? And material wise, if you see, so many kinds of materials are used. NV, nitrogen vacancy centers are used in diamond, ion traps are used, quantum dots are used, different isotopes of silicon. So 28 silicon, okay? Silicon 28, it is also an isotope of silicon that is used for as a quantum material. Two-dimensional materials by confinement, neutral atoms, right? Many kind of heterogeneous structures, superconducting circuits. So these are all materials that are used to form this kind of devices or qubits which can be used for these applications. Okay, so this is what this map is trying to show. Okay, quantum computers. Probably I'll just go through this one. Quantum sensing. Okay, so I think I've briefly touched upon all of them. So yeah, quantum sensing is not only limited to, let's say, any general sensing, but it is also important in, for example, medical sensing. So MRI, magnetic resonance imaging. Even there you find application of quantum sensing. Okay. Quantum communication, I already said how laser-based quantum key distribution, quantum cryptography, teleportation, they are all possible through quantum communication. Quantum memory is another application, and there what is used is the coherence, or what a important parameter there is the coherence time. I don't know if you have heard about it. So what happens is, for example, this is the qubit, okay? When I write the qubit, however I write it, I've written it in between the, my write and my read, will the states be coherent? Will it remain in that state? That is quantum coherence. Okay. Now the idea is therefore to what should happen? Quantum coherence, this coherence time. Should I try to increase the time or not? Yes or no? Yes. So the coherence time has to be increased, and that is a very important area of research in quantum materials. How the coherence time can be increased. Now I will just relate this to the spin discussion we had. Now I told you it's a superposition state, and let's say that if I probe it, it's superposed. But if I probe it, let's say it ends up in this orientation. Okay, this is the state it collapses into. Now before that, it was in a superposition state, right? If my material has high coherence time, then this spin, every time I probe it, after like after a few seconds I'm probing it, every time it should collapse into this. It is superposition. The moment I probe it, it should collapse into this state. Then it is coherent, right? If in between at some point it collapses into this state, then it is non-coherent, correct? So my memory is lost. Right? Again, I have stopped probing it, it should again go into superposition state. So it's a mixed state. The moment I start probing it, again it should come into this state. Every time it should come into this state. Then it is coherent. Have you been able to grasp the concept of coherence here? Okay. So, because sometimes when I studied it initially, I was like, it is superposed, again it is coherent. How is it possible? It is possible. Because coherency is only, comes into picture when you are probing it. The moment you probe it, it should land up in the same state every time. Then it is coherent. But other than probing, it will always be superposed. In quantum realm, it will always be superposed. Okay, fine. This one quantum materials. Okay, so this is another chart I have borrowed. Yeah.
Regarding the reading and writing of the qubit, the reading is observing.
Correct.
Writing is also observing.
No, writing is changing in the state. So once I have written it, then every time, say it was like this, every time I'm probing it, it should be like this, so it is coherent. Now I want to change it, right? So I have stopped probing it, now this is in this state, okay? Now I will write it in a way that now it is like this. Now when I start probing it, before probing it will again be like this, but now I start probing it will be like this. Every time I probe it, it will be like this. So writing is different. Okay, but the moment you are not writing or reading, it will always be in a supervised system. Okay, so I mean, if just one thing I want to write here, probably just relating to this discussion. So when I say superposition state, the state will be something like this. So it is A. Let's say I am talking about this state here plus B. So this is is the down probability up or down function, up function, and it is there are two coefficients which is relating them. Okay. So this is superposition of two states, right? This is what I mean by superposition. Okay, so these are different kinds of quantum materials that are used. Some of them you may have heard, some of them you may not have heard, but I will just mention the names. So there are something called wire semimetals, topological insulators, I already mentioned in this lecture. Superconductors, then you have quantum liquids, right? So these are all different materials that are used for different kinds of applications. So these are the interactions, this is the physics of it, or the properties of it. These are the products or the devices, and these are the materials. Okay. Okay. Fine. So I think I will stop here. I have already discussed topological insulator, but I will just why I put it here is that topological insulation is a quantum property, and I just wanted to relate to the spin talk before that they are actually interrelated. The spin and the spintronics that we do is also at some point related to the quantum world or the quantum properties. Okay, because of these quantum properties, we actually have the topological insulation properties or topological surface states and so on. Okay. Alright, so I'll just skip through them because we already discussed that. Okay, I think I'll end my talk here. I'll not discuss anything more. Yeah, if any further questions, please ask. And if you don't have it now, we can always take it during lunch or even after that. Feel free to contact me. You can have my phone number, email ID, whatever you want, LinkedIn, whichever way you want to connect. I would be always happy to collaborate with you and build more fruitful, meaningful relationships. So, any questions? Yes.
Can you think of the Schrodinger's cat problem as the coherence problem?
Coherence problem. Yes, exactly.
Once I observe the cat, if it is there, second time I observe it, it should be always there.
If it is coherent, if the system is coherent. See, the Schrodinger's cat or the box doesn't guarantee you coherency. It just says that the moment you are observing it, then it is in a particular state. Before that, you don't know what state it is. But every time you probe it, will it be in the same state will depend if it is coherent. Now, many of the, or in fact, most of the materials are non-coherent. The challenge is to make them coherent. That's the quantum world, it's non-coherent. But we are trying to make it coherent.
If it is not coherent, then God does not exist.
Uh, yeah, so that's why Albert Einstein never agreed that this is possible. No? So, although he received his Nobel Prize for photoelectric effect, and because of that research, we are bound to believe that particle wave duality and everything. But actually, till his last moment, he never believed that the quantum world is probabilistic and not deterministic. He never believed. He is one of the greatest minds of this previous century, but he never believed. So I think all of us, even today, we have a very difficult time believing that it is probabilistic. But unfortunately, it is, and it is experimentally proved now. Okay, and this the last straw in this, experimentation was actually done in 2014 or 13, I forgot, when we actually proved we were able to isolate a single photon and then establish the wave particle duality. Because see, before this wave particle duality always was done in bulk. We could never have one photon and ensure that it is light and wave at the same time. Because we could not generate a single photon. We always generated them in bulk. 2013 or 14, I forgot. In Europe, they were able to do this experiment with a single photon. And again, all doubts were then finally rested that even a single photon has both wave and particle. Because before that, there was still a doubt. Is it like a collective behavior that they start this wave phenomenon only when they are in together, and maybe individually they are not? But no, it was found finally that even two single individual photons can interfere. That was found. Okay. So interfere means again wave, right? So it is now proof beyond doubt. Unless something very groundbreaking research comes which completely turns it upside down, so far we have to believe that this is true. Although we find it difficult to believe it, but it is true. Okay. Okay. Any questions? Practical method. Can you please elaborate the question?
Means creating some products.
Okay.
Say for example, quantum
Quantum dot
transistor.
transistor. Okay.
How this practically
How does practically make?
one process by one method.
So I discussed that I mentioned there are also three kind of methods I have mentioning here. Maybe there are more. So one can be by lithography. I make very small island, maybe 1 nanometer, let's say, or maybe less than a nanometer wide or circle, something like that. So that is quantum confinement already, and that would probably have very few electrons. Right, that's one way. The second one can be Coulombic, that I flood everything with different kind of charge. In between, I have something which is neutral, and probably that is the barrier already, energy barrier, so quantum confinement. The third one can be my material, heterogeneous way. So I have everywhere I put a alloy or a material somehow, the material property is different, and in one single region, the material property is different. So that way I can make. But if and so I hope I've been able to answer. Okay. And the challenge there would be in lithography and all those kind of methodologies how to do it. But good thing is that we have really evolved and we are now able to do remarkable small dimensions. I mean, when I say we, I mean humanity. I am not able to do it. In India, we are not able to do it, but humanity as a whole is able to do it. So that's how we are able to realize all those quantum transistors. And quantum dots are actually done everywhere. Even in IIT Guwahati, quantum dots are done. Quantum dots is very, say, is well researched topic already. So if you are interested in quantum dots, you might also find some people who are working in IIT Guwahati quantum dots. You can always build a collaboration. But quantum dots is well researched. Quantum transistor, I agree, is not so much. Any questions? Okay, if no further questions, I would just like 2 minutes to stop. You have something? No, right? First thing is, I would take this opportunity, therefore, to invite you that we can have, build up more collaborations, right? And how I propose is that, see, I get a lot of emails from even in your college also for internships, right? But the problem with this is that I have talked to some of them, and mostly they come for this internship because it is a compulsion imposed. I think on the seventh or eighth semester, something like that, right? So it's a compulsion. They have to do it. So they come and they mail, and they are not very interested. Let's say, and that when that happens, it is difficult. Why it is difficult is because see, in a industry, probably it doesn't matter. But for us, we don't have so much manpower that to guide a student, and if that student is not motivated, it becomes very difficult for us to really have a meaningful, thesis or a report out of that internship, right? So that's why I am very skeptical generally, and this is my personal case. I don't know about others of taking students without having some reference from someone. So, if you are interested in building a research collaboration or something, or if you want your students to learn something like that, what we can always do is you can always refer some students directly. That these are the students we think they are interested in this and this, and through them we can learn this. We can do this research together. Maybe this kind of things. Let us please propose, and I can always come over. You can also come over. We can meet. We can meet the student together, and I think that way we can do a lot of meaningful work. So not only the student gets an internship, but I think all of us will learn something new, publish something, so that will help us. Okay. So that is my proposal. Please see if you like that. Second thing I think is that I would urge you that if you can encourage your students to prepare for the GATE exam, because we always look for bright students for PhD. And unfortunately, I would like to say that very few students from Assam or Northeast together turn up for PhD. We always want that more students show up from local because that is an important mandate why IIT Guwahati was built up. Otherwise, there are so many IITs. IIT Kharagpur is there. Why build up IIT Guwahati to develop this region, right? And that human development can happen if these people come to us. And so you are very bright students. Please encourage them to appear for the GATE exam. And after the GATE exam, they can always appear for a direct PhD admission into IIT Guwahati without a master's, right? So please let your students know. This will be very helpful for them also, and I think helpful for the region also. Okay. And next is workshops and conferences. We can always think about joint workshops, conferences together. Maybe we can take some other universities in the fold also which are there in Assam or locally, and we can organize joint conferences and workshops. Maybe all of us will get to learn from each other. Okay, so these are my proposals. Please feel free to contact me. My email ID cannot be seen very clearly, but it is very simple. Tanmay.datta, Tanmay dot DUTTA@iitg.ac.in. You can always find it on the IITG website also. My website, my personal website also, tanmaydatta.com. You can find it there. And if you need my phone number, please let me know during lunch. I will happy to share my phone number as well with you. Or I can, if you want, I can also say it here. You need the phone number or email ID is enough? Okay. I will write on the board then. Sorry, this slide I think is not visible clearly, so I will write it here. So the email ID is TANMAY dot DUTTA at the rate iitg.ac.in. Phone number is 8812001780. I will erase the rest of it so that it is. Is it visible? Okay. Okay. So thank you so much for being such a nice audience. Uh, so many interesting questions, so many inferences actually you drew without me telling it. So really nice to interact with you today. I look forward to more interactions in the future. Thank you and all the best to all of you in your in this new year and your future ahead. Thank you.
Thank you, Dr. Sharma, for the excellent talk. Now, there is an important announcement.